Good day, learners. Welcome to our physical sciences lesson. My name is Aminim Kize. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Right, grade 11, our focus is on knowledge area, electricity and magnetism. And then under electricity and magnetism, our focus will be electromagnetism. Right, so according to our exam guidelines, this is what we need to cover. And electromagnetism, magnetic field associated with current carrying conductors. Use the right-hand rule to determine the magnetic field associated with a straight carrying current conductor, current carrying loop, a solenoid. Draw the magnetic field pattern around a straight current carrying wire, current carrying loop, a solenoid, and also state Faraday's law as the magnitude of the induced EMF across the ends of the conductor is being directly proportional to the rate of change in the magnetic flux linkage with the conductor. Use weights and pictures to describe what happens when a bar magnet is pushed into or pulled out of the solenoid connected to a galvanometer. Use the right-hand rule to determine the direction of the induced current in a solenoid when the north and the south pole, or the south pole of the magnet inserted or pulled out of the solenoid, right? So, and also define the magnetic flux, calculate the induced EMF using the equation E equals to negative N change in magnetic flux, divide that by change in T, where phi is BA cos theta. So, but today, grade 11s, we are not going to focus on the calculations. The only thing that we are going to focus on is the magnetic field, for current carrying conductors, and also drawing the magnetic fields, right? Patterns around a straight current carrying conductor, and then a loop, and also a solenoid, and also more. On this, I want us to talk more about this too, because I think they're a problem in most cases. Use weights and pictures to describe what happens when a bar magnet is pushed into or pulled out of the solenoid connected to a galvanometer, right? And also use the right-hand rule to determine the direction of the induced current in a solenoid when the north or the south pole of a magnet is inserted or pulled out of the solenoid. So it's what we are going to focus more on, right? Then these are the important terms or definitions when it comes to this topic, although I'm not going to go through them now, right? But it's going to be the magnetic flux, and then how to represent the magnetic flux. We use phi, so this symbol is phi, right? So phi is the symbol for magnetic flux. We are going to talk more about that. Faraday's law, magnetic field, a solenoid, electromagnet, EMF or induced EMF. So those are the important definitions when it comes to this topic. So as we move on, we are going to introduce them, all right? Then let's start with the direction of the magnetic field around a straight current carrying conductor, all right? So what is important here, learners, is that already after this topic, according to our ATP, we will be doing your electric circuits, right? Even in grade 10, you did electric circuits, right? So already we have talked about current. You know what is current. Remember, current is the rate of flow of what of charge, and which is calculated using the equation I equals to what Q over change in T, where I is the current in amperes, and then Q it's what is the charge which is measured in coulombs, and then change in T obviously is the change in time measured in what, in seconds. All right, so that is current. It's what you did in grade, even in grade 9 if I'm not mistaken, you did talk about current. Same even in grade 10 you did talk about current, right? So what is important here is that when there's current that is flowing through the conductor, so you should know that around that conductor there is magnetic field. Okay, so now what is important, already I've introduced the term magnetic field, so you didn't talk about that in grade 10, right? But what is magnetic field? Magnetic field is the region in space where the electromagnetic or the ferromagnetic material experiences a force, right? So when you talk of the magnetic field, that is the region in space where a ferromagnetic material or a magnetic object would experience a force. So what you need to know is that when it comes to a carrying conductor, there is magnetic field around that current carrying conductor. For example, here, when you look at this, a straight conductor, so this is a straight conductor, right? So there's current that is flowing through this straight conductor, okay? So as long as there's current that is flowing through that straight conductor, right, around it, you should know that there is magnetic field, okay? So around a straight current carrying conductor, there is magnetic field. As you can see here, these lines, these are magnetic field lines. So the magnetic field lines, they represent the magnetic field, which is the region in space where the ferromagnetic material will experience a force. So around a straight current carrying conductor, there is magnetic field. So this is a straight current carrying conductor. It's a straight conductor, right? And there's current that is flowing through that conductor. So around it, you should know that there's magnetic field, right? So now, what is important here is you have seen those lines. Those lines, they represent the magnetic field. So these are magnetic field lines that represent the magnetic field. Remember, we've talked about the electric field lines when it comes to your electrostatics, right? And we've even talked about the properties of electric field lines, right? One of the important properties there is that when you draw these lines, you have to make sure that they don't touch or cross each other. It's the same thing even when it comes to magnetic field. So when you represent the magnetic field, please make sure that the lines that you draw, they don't cross, they don't touch each other, right? And with the electric field lines, remember they run from from the positive charge to the negative charge, and if you still remember, to determine the direction of the electric field, there we use the positive test charge, right? So when it comes to magnetic field, we are using the same properties of field lines. So when you draw the field lines, please make sure that the field lines, they don't cross or touch each other, all right? And then to represent the strength of the field lines, for example, whether it's magnetic field or electric field. So when the lines are close together, it means that the magnetic field around that point is stronger, right? And then when the field lines are far apart, it means that the magnetic field is it's weaker, all right? So same thing even when it comes to this topic. It's just that here we're talking about the magnetic field, which is the region in space where the ferromagnetic material will experience a force. What type of a force? The magnetic force, obvious, right? So when you draw the lines, please make sure that they don't cross, they don't touch each other. And then where they're close together, we must understand that the strength of the magnetic field there is stronger, right? And then where they are far apart, the strength of the magnetic field is it's weaker. Those are some of the important things there. But now back to the straight conductor with the current that is flowing through it, right? So what we know by now is that around that straight conductor there is magnetic field. So these lines, these blue lines, as you can see, these blue lines, they represent the magnetic field. That is very, very important. Okay, so now another thing which is very, very important when it comes to this, right, is the direction of the current, right? So if we can check here, when it comes to this straight conductor, the direction of the current here is out of the page, all right? So it's out. So if the arrow is facing up like this, so it means that it's out of the page. So since I'm using the screen here, it means that it's out of the screen, all right? So then if I can have another conductor, this is another conductor, for example, and then this is the direction of the current. It means that it's into the page, right? So it's into the screen because I'm using the screen. So here it's out of the screen. That will be the direction. All right. Then for this one will be into the screen. That is the direction of the current. But what is important is that as long as there's current that is flowing through this straight conductor, around it there is what? There is magnetic field. Okay, so another thing which is important here now, already I've talked about what the direction of the current, whether the current is into the page or out of the page. Since I'm using the screen, so it's either into the screen or out of the screen. So for example here, that this is out of what? Of the screen, all right? And then this other example here is what? Is into what? Is into the screen, right? Then now we need to determine the direction of what? Of the magnetic field. Okay, we need to determine the direction of what? Of the magnetic field. Is it clockwise or anti-clockwise? All right, around a straight conductor, is it clockwise or anti-clockwise, the direction of the magnetic field? And to determine the direction of the magnetic field, we use what we call right hand rule. Okay, we use right hand rule. So with the right hand rule, you have to use your right hand. Okay, so you use your right hand. Okay, so this is my right hand. Okay, so here in what is important is the thumb and the curled fingers. All right, so when you are talking about a straight conductor, you want to to determine the direction of the magnetic field, right? We are using the right hand rule, right? So two important things, your thumb and the curled fingers, right? So your right thumb, right, is in the direction of what? Of the current, whether it is out of the page or into the page, right? Out of the screen or into the screen, all right? So the thumb is in the direction of what? Of the current. Okay, then the curled fingers, the direction of the curled fingers is actually the direction of what? Of the magnetic field. Okay, so one, for you to be able to determine the direction of the magnetic field, one, you should know first the direction of the current, whether the current is into the page or out of the page, because you'll be using the page. All right, so obviously your exercise book is on top of the table, right? So if it's into, it means that you are pointing what? Your table, or you are pointing your book, right, or the paper, using your thumb. But which thumb? Remember, you are using your right hand. Ne? Then if it's out, obviously it should be your thumb should point away from the table or away from what? From the book that you are using. So since I'm using the screen here, it's either into the screen or out of the screen. Okay, so that is the first thing that you need to know, the direction of what? Of the current. Then after getting the direction of the current, how do we get now the direction of the magnetic field? Still, we are using what? We have to use what here? The right hand rule. With your right hand rule, the thumb is always in the direction of the current, and then the curled fingers are in the direction of what? Of the magnetic field. For example here, for this one, right? Right, what I have there, the current out of the page, or out of what? Of the screen. So look at the curled fingers. So the curled fingers are pointing in which direction? Is it clockwise or anti-clockwise? Obvious, in this case, it's going to be what? Anti-clockwise, as you can see on that screen. All right, so how do we determine the direction of what? Of the magnetic field? We use right hand rule. But first thing that you need to know is that around a current carrying conductor, there is what? There is magnetic field. Okay, so for you to be able to determine the direction of the magnetic field, you use right hand rule. The thumb is in the direction of the current, and then the curled fingers are in the direction of the magnetic field, right? So current in or out is what you need to check. So in this case, the current is what? It's out of the page. Okay, the current is what? Is out of what? Is out of the page. Okay, so if it's out of the page, it means that your thumb should point away from the page, all right, or from the screen. Okay, then look at the direction of what? Of the curled fingers. They are anti-clockwise, right? But for this one, so let's say this is the direction of what? Of current. So in a straight conductor. Okay, obvious, I know that here there will be what? There will be a magnetic field around it. Okay, so this is my the conductor. Let me just do this. So this is the conductor. Then I have the direction of what? Of the of the current, which is into the page. So I know as long as there's current that is flowing, then there will be what? There will be a magnetic field. So this is the direction. This is into the page. Okay, so then I know that there will be what? There will be magnetic field. So how do I get the direction of the magnetic field? I use my right hand, right? So the direction of the current is into the page. So look at my curled fingers. So the curled fingers, they're in a clockwise what? Direction. So they're in a clockwise what? Clockwise what? Direction. So this is the clockwise what? Clockwise what? Direction. So this is how we determine the direction of what? Of the magnetic field around a straight current carrying what? Conductor. Okay. Then another thing, so I think I will talk about this when it comes to what? Now a loop. So now let's look at okay, maybe before we look at the loop, all right? So we have talked about the straight conductor. As long as there's current that is flowing through it, there will be magnetic field around it, right? And then how do we determine the direction of that magnetic field? We use your right hand what? Your right hand rule, right? So check what is happening here. The current here is out of the page. So it's face, look at your thumb, This is how you need to hold your what? Your conductor. So it's out. So look at the curled fingers. So the direction of the curled, these are your curled fingers. So this is the direction of what? Of the magnetic field. Okay. Then another thing which is very, very important is that the field is strongest close to the wire. So the field is strongest close to the wire, and that it weakens as the distance as the distance from the wire increases. So which means that when you draw the magnetic field lines, you should know that if this is your conductor, right, the field lines should be close together here next to the wire, right? And as you move away from the wire, then the field lines should be far apart, to show that you understand that the magnetic field is stronger closer to the wire, but it weakens as the distance from the wire increases. That is another thing that is very, very important. Okay, then now let's come to a loop. So we are talking about a straight conductor. Now we are coming to what? To a loop. So a loop, it's a coil of what? Or a loop of a single wire. All right, so it's a single wire, right? Now we want to determine the direction of what? Of the magnetic field. Okay, so you can see that this is a loop, right? Okay, so this is a loop. So this side, you are given the direction of current. Obviously, if the current is in this side, then this side the current is going to be what? Out. So it's, this side is into the page, right? And then this side is what? Is out of the page. Remember, this is what now? This is a loop. It's unlike when it comes to a straight conductor. Okay, when it comes to a straight conductor, this is a straight conductor. Okay, if I do this, it means that this is what? Out of what? Out of what? Of the page. But if I do this, this is a straight conductor again, and then I do this, this is into what? Actually into what? Into the page, right? So I have a loop here. The current is in this side, and then the current this side is what? Is out. So into the page, out of what? Of the page. So now I want to determine the direction of the magnetic field, but I know that because there's current that is flowing, already there's what? There is magnetic field. Even this side, there is what? There is magnetic field. It's just that now the direction is not the same. The direction this side is in, and then the direction this side is what? It's out. So obvious, the direction of the magnetic field is also going to do what? To change. Okay, so the current here is in. All right, so it's into the page. Okay, and then this side the current is what? Is out of what? Out of the page. Okay, so if it's into the page, another way of representing current into the page, we use a cross. I hope you can see that. Ne? So if you see a cross, already we are given the direction of the current. The current is into the page, okay? And then if you are given a dot, the current is out of the page. So it's into the page, the cross, so it's into, and then the dot is out of the page. Okay, so here we have a loop, right? And then in this loop, there's current that is flowing. So if there's current that is flowing, obvious there is what? There is magnetic field. But now we need to determine the direction of the magnetic field. So unfortunately, it can't be the same on both sides, because if you look at this side, the current is in, but this side, the current is what? It's out. Okay, so in and out, we can represent current into the page using a cross, and then current out of the page using a dot. So please, let's not confuse the two. So if you see a cross, it means that the current is what? Is into the page. If you see a dot, it means that the direction of current is what? Is out of the page. So if I say into the page, right? For example, here, this side, so it's into the page, which goes together with this diagram, right? So this is into the page, okay? Look at the direction of the curl fingers. So the curl fingers, they're in a clockwise what? A clockwise what? Direction, okay? So the current into the page, so this is the direction of what? Of the magnetic field, which is going to be what? Clockwise. Then the dot represents the current out of what? Of the page. So out, it means that my thumb should face out, right? So out of the page, look at your curl fingers at home. You'll be able to, I think it's better if you do this on your own. So the thumb is out of the page, right? So it's facing up as I speak, right? So it's out of the page. The page is on top of the table, then you're saying out. Obviously, your thumb should point away. If I say into, so it should point towards that page, okay? But remember, you're using your right hand, okay? So let's look at out of the page. So it's out of the page, and I'm looking at my curled fingers. So the curled fingers are in this direction, which is the anti-clockwise what? Anti-clockwise what? Direction. So when it comes to a loop, right? There's no way that you'll get the same direction for what? For the magnetic field. So where the current is in, then the direction of the magnetic field will be clockwise. But where the current, which is this side, side B, where the current is out, then the direction of the magnetic field is going to be what? Anti-clockwise. So that is a loop, okay? And a loop, it's a loop of what? Of a single wire. So this is a loop, right? And then this is what? A straight conductor. So what is important here is that please note that when it comes to a current carrying conductor, there's magnetic field. And if there's magnetic field, obviously they will ask you to determine the direction of the magnetic field. And how do we determine the direction of the magnetic field? We use right hand rule. And when you use right hand, let's not forget the thumb is in the direction of current, whether the current is in or out, right? And in, we can represent that using a dot. And then out of the page, we can represent that using what? Using a cross. Then look at the direction of your curled fingers. For current into the page, you'll see the direction of your curled fingers will be clockwise. And then when the current is out, which is this part, the direction of what? Of the magnetic field will be what? Anti-clockwise. So that is the magnetic field around a current carrying what? Conductor for a loop now. Okay, then we have talked about the straight conductor, a loop. Now let's move toward a solenoid. All right, so a solenoid is a what? It's a loop of many what? Wires. Okay, as you can see here, right? So there are so many. It's unlike, this is a straight conductor. This is a loop, right? And then you have what? A solenoid, something like this, right? So still, even when it comes to a solenoid, right, we are still using right hand rule to determine the direction of what? Of the magnetic field. Okay, we are using right hand rule to determine the direction of what? Of the magnetic field. So here they've defined a solenoid as a set of tightly wound insulated wire that forms a cylindrical coil. Okay, so this one is a coil of many what? Loops. That is a solenoid, ne? A coil. You can see there's so many loops here. It's unlike a loop which is just a single wire, okay? But here there are so many loops, which forms what we call a solenoid, right? So now we want to check now the direction, or to determine the direction of the magnetic field when it comes to a solenoid, right? We have talked about the straight conductor, the loop. What is important? First thing, determine obviously they will give you the direction of the current, whether the current is into the page or out of the page, right? So if they say into, sometimes they won't write it in weights. They will just use a cross to say the current is into, right? And then if it's out of the page, they can write it in weights, or they can give it in weights, or they can just say draw what, for example, they can just give you a dot. So immediately when they give you a dot, they assume that you already know that a dot represents the current out of the page. Dot out of the page, cross into the page. I hope it's clear, right? So now let's look at the direction of the magnetic field when it comes to a solenoid. A solenoid is it's a wire of many loops. You can see there's so many loops here, right? So already, remember, what produces the magnetic field is the current. So current produces what? The magnetic field. Okay, so already here when it comes to this loop, sorry, this solenoid, already here what are we having? We are having what a current, right? So for example, let's say you have a battery here, you have your what here, your negative terminal, and your positive what? Your positive terminal. And the conventional current flows from a positive terminal to a negative terminal. So this is the direction of the flow of what? Of current. So already here we have current that is flowing through this solenoid, okay? So if already there is current, obvious, around this solenoid, there will be what? The magnetic field. But now we want to determine the direction of this magnetic field. Okay, how do we determine the direction of the magnetic field? Still, we use right-hand rule. But now the problem when it comes to a solenoid, remember, when it comes to a straight conductor, as a loop, the thumb is in the direction of current, whether it's in or out of the page. The curl fingers are in the direction of what? Of the magnetic field. But when it comes to a solenoid, it's vice versa, right? The thumb is in the direction of the magnetic field, all right? And then the curl fingers now are in the direction of what? Of current. So please be careful when it comes to a solenoid. As much as we use right-hand rule, but the thumb now is in the direction of the magnetic field. So wherever your thumb is pointing, it should point the North Pole. It means that on that side we are having what? The North Pole. Then the curl fingers are in the direction of what? Of the current. Okay. Thumb is in the direction of the magnetic field. So wherever your thumb is pointing what? The North Pole, right? And then the curl fingers are in the direction of what? Of the current. Okay, so let's check here when it comes to this diagram. The current, you can see here, it's in, right? This side in, right? And then this side obvious, then the current obvious is it flows from a positive terminal to what? To a negative what? Terminal, right? So you use your right hand. So it means that you need to hold, you know, your what? Your solenoid, right? And when you hold it, right? So check bullet number 3. What are they saying there? Hold the solenoid in your right hand with the bent fingers pointing in the direction of the conventional current. Pointing in the direction of the conventional what? Current. The thumb points in the direction of the North Pole of what? Of the solenoid. So now things have changed. As much as we use the right hand, but the thumb now is pointing in the direction of the North Pole, or is pointing North Pole, right? Which is the direction of the magnetic field. And then so the thumb is always pointing the North Pole, and then the curl fingers are in the direction of the conventional current. As you can see how, look at the picture, okay? So the thumb, the way they are, actually the fingers, the way they are bent, they follow the direction of what? Of the current. You can see on the picture, they follow the direction of what? Of the current, right? So when you use your right hand, when it comes to a solenoid, the thumb, remember, the thumb is always pointing your north. And then, but remember, what are we looking for here? Is the direction of the magnetic field, right? We are looking for the direction of the magnetic field around a solenoid, okay? So obviously, they need to give you what? The direction of what? Of the current. They need to give you what? The current, right? and also obvious the direction of what of the current, right? Because remember, what produces this magnetic field is the current that is flowing through that conductor. Okay, so around a current carrying conductor there's a magnetic field, but now we want to determine the direction of the magnetic field. How do we find this direction of the magnetic field? First thing that we need to do is to determine the direction of the current. And if there's a battery here, or yes, if there's a source of power or a battery here, right, then you know conventionally current flows from a positive terminal to a negative terminal. So if this is positive this side, then this is how the current is going to flow. Now I want to determine the direction of the magnetic field, but first thing that I need to do is to determine the direction of the North Pole. So how do I determine the direction of the North Pole, right? So when I hold my solenoid, it means that the way my fingers are bent, right, they should follow the direction of the conventional current. So just see on that diagram, you can see the way this solenoid is, the solenoid, look at the solenoid, the bent fingers are following the direction of what? Of the conventional current. And then look at the thumb here. The thumb, where it is facing, it means that this side we are going to have what? The North Pole. And then if it's not obvious, this side we are going to have what? The South Pole. But what is important? Now the thumb is always pointing in the direction of the North Pole. And the fingers, the way you bend your fingers, make sure that they follow the direction of the conventional current. I hope it's clear, right? They follow the direction of what? Of the conventional what? Current. Then from here, you can draw the magnetic field lines, right? How are you going to draw the magnetic field lines? This is how you need to draw your magnetic field lines. Already this side, you know, there's north and then there's south. And then magnetic field lines, they run from what? From North Pole to what? To South Pole. So you can see here, from north to what? To south. So north to south, north to south. Even this side is north to what? To south. Okay. So these are some of the things that are very, very important. Okay. So a solenoid, please, let's not forget that thumb is pointing the direction of the North Pole, and then the fingers, the curl fingers, they are always in the direction of the current, or the conventional what? Current. So that is the magnetic field around a straight conductor, magnetic field around a loop, and magnetic field around what? A solenoid. Let's not forget that. Those are some of the things that they will ask you when it comes to an exam, and you need to understand them. If you don't, we are here to assist you. All right. Then now let's look at the electromagnetic what? Induction. When we talk of electromagnetic induction, what are we talking about? Already we know that as long as there is current that is flowing through a conductor, whether it is a straight conductor, whether it is a loop, whether it is a solenoid, as long as there's that current that is flowing through, then magnetic field will be what? Will be induced. All right. So that induced magnetic field, right? How do we find the direction of it? We use right hand rule. And for a straight conductor and a loop, the thumb is in the direction of the current, whether the current is in or out. If the current is in, remember we use what? A cross, right? To represent the current that is into the page. We use a dot to represent the current that is what? Out of the page. That is the thumb, which represents that when it comes to a straight conductor and a loop. When it comes to a solenoid, right, we still use our right hand, right? But now the thumb is always pointing, right? The thumb is always pointing what? The North Pole, okay? Or the direction of what? Of the North Pole, okay? Then the fingers, which is your curl fingers, the way you bend them, they should always follow the direction of the conventional current, which is from positive terminal to what? To negative terminal. Right. Now we are looking at what? Electromagnetic what? Induction. Already, a current, which is the rate of flow of charge, induces the magnetic field. Already we have talked about that. Ne? So what produces the magnetic field is the current, right? So similarly, a changing magnetic field induces an electric what? Current. And this is what we call electromagnetic what? Induction. Okay? So now, initially, we were talking about what? The current, right? Which induces what the magnetic field around a conductor. Okay, so remember that that magnetic field is induced if and only if there's current that is flowing through. Okay, similarly, when it comes to what now, you have the magnetic field, right? It is also possible to produce current through what the magnetic field. So it's other way around, right? And this is what we call electromagnetic induction. So when you talk of electromagnetic induction, right, we are inducing what current in a conductor using the magnetic field, right? Or using the changing, not just magnetic field, but using what? The changing what? Magnetic field. So changing magnetic field induces what? The electric what? Current. So what induces, what produces the current? It's actually, remember, initially I said the current, when I was doing those three scenarios, the straight conductor, the loop, and also what and also the solenoid. I was using a source of power, which is the battery. That will produce the current. And if there's current that is flowing, then there will be magnetic field. But now what am I doing? Right, when it comes to, or what are we doing when it comes to electromagnetic what? Induction. We want to produce current using the changing magnetic field, right? So according to Faraday, right, as long as there is that relative motion, as long as there is that relative movement between the magnetic field and the conductor, current is induced in that coil. So now what will be the source of current, right? The source of current or electric current now will be what? Will be the magnetic field, right? Not the source of power, which is what? The battery, for example. Okay, so according to Faraday, we can produce current, right, using the changing what? Magnetic field. And that is what we call electromagnetic what? Induction. So according to Faraday, as long as there is that relative motion, as long as there is that relative movement between the magnetic field and the conductor, current will be induced or will be produced in what? In that coil or in that conductor. And that is what we call electromagnetic what? Induction. So with electromagnetic induction, we are inducing current in a coil using the changing magnetic field. That is simple what? Electromagnetic what? Induction. We are inducing, we are producing electric current using the changing magnetic field. And what produces the magnetic field is the is in this case now will be what? Will be your magnet, right? So what are we having here in this picture? This is electromagnetic what? Induction. But what are we having here? We are having a bar magnet that is going to produce the magnetic field. Okay, but remember, initially we are producing magnetic field using current. Now we want to use the changing magnetic field to produce the electric current. I hope it's making sense. Okay, so it's other way around now, right? So what are we having here? Right, we have a solenoid, right? Solenoid, right? And then we are having a bar magnet. And what are we having here? We can say this is a galvanometer. So a galvanometer is an instrument that is used to measure very small current and potential difference. That is a galvanometer. Okay, so to measure very small current and voltage or potential difference, we can't use those normal ammeters or voltmeters. We need to use the galvanometer. So galvanometer is an instrument that is used to measure very small current and potential difference or voltage. Okay, so what are we having here? We are doing an experiment, right? So we are having an experiment here. What are we doing here? It's electromagnetic induction. We want to induce current in a coil using what? The changing magnetic field. Okay, right. So this is how we have connected our apparatus. So we have a solenoid there, right? And then the solenoid is connected to what? To a galvanometer. And then there's also what? A bulb. Okay, so what is the function of this bulb, or what is the function of this galvanometer? Is to check if current is induced or if EMF is induced in what? In a coil. Okay, so obvious, if EMF or current is induced in a coil, what is going to happen? This nickel, this galvanometer nickel is going to deflect to show that there is current or there's potential difference that is induced in what? In that coil, okay? And in addition to that, if it deflects and if it's enough, right, then what is going to happen to this bulb is going to glow to show that current is what is induced in what? In that coil. So this is simple what electromagnetic induction. So we want to produce current using the magnetic field, but not just magnetic field, changing what? Magnetic field. So this is how we have connected our apparatus. All right. So now, one, if the magnet is stationary, right? If the magnet is stationary, it's not moving, right? The galvanometer nickel does not deflect. If it doesn't deflect, it means that there's no current that is induced in that coil. Why there's no current that is induced in that coil? Is because there's no relative what? Motion. According to Faraday, as long as there's that relative motion or movement between the coil and the magnetic field, EMF will be induced in that coil. So if in this case, both the coil or the solenoid and the magnet, they are stationary, right? So if these two apparatus are stationary, then there will be no deflection in the nickel of what of the galvanometer. All right, so the galvanometer nickel won't deflect to show that current is not induced. Okay, but something was observed, right? If you move the magnet in and out of the coil, in and out of the coil, the galvanometer nickel deflects, right? The galvanometer nickel deflects. What causes that galvanometer nickel to deflect? If it deflects, it shows that there is current or the potential difference that is induced in what? In a coil. So initially, if both the coil and the magnet are stationary, there's nothing that is happening, right? The galvanometer remains as it is. There's no deflection, which shows that if there is no relative motion or movement, current is not induced, will not be induced in what? In a coil. It is only induced if there is relative movement, right? So for example, if you push this magnet in and out of the coil, in, out of the coil, in and out of what? Of the coil, what is going to happen? The galvanometer nickel is going to do what? To deflect. So when it deflects, it shows that what is this? Current is what is induced in what? In a coil. So straight carrying conductor and the solenoid, the opposite of each other when it comes to the direction. Yes, that is true. Anonymous, that is true. For a straight conductor, as much as we are using the right hand, right? But now for a straight conductor, thumb is in the direction of current, curl fingers are in the direction of the magnetic field. But when it comes to a solenoid, the thumb is always pointing the direction of the North Pole, and then the curl fingers are always in the direction of the conventional what? Current is always the case. As much as we are using the right hand, but curl fingers for the solenoid is the direction of the current, but when it comes to a straight conductor, is the direction of what? Of the magnetic field, right? So here is electromagnetic what? Induction. So with electromagnetic induction, no current is induced in a coil if there is no relative motion. Current is induced in a coil if there is only relative motion between the coil and what? And the magnetic field. So if I push the magnet in and out of the coil, what is going to happen? The galvanometer nickel is going to deflect to show that current is induced in what? In a coil. So if it's enough, then what will happen to that bulb? The bulb is going to do what? To glow. But if the coil or the solenoid and the magnet are both stationary, nothing is going to happen. EMF is not induced in a coil, or current is not induced in what? In a coil. So current is only induced in a coil if there's changing magnetic field, or if there's relative motion between the coil and what? And the magnetic field. It's when the current will be induced in what? In a coil. I hope it's making sense. All right. So this is what was observed by Faraday, right, when he was doing this experiment, right? So if the magnet and the coil are both stationary, or if there's no change in magnetic field, then there's no current that will be induced in a coil. Current is only induced in a coil if there's motion or if there's changing magnetic field. So, for example, if I push this magnet in and out of the coil, in and out of the coil, the galvanometer nickel is going to do what? To deflect. And as it deflects, it shows that current is what? Is only induced in a coil if there's changing magnetic what? Field, or if there's relative motion between the magnetic field and what? And the conductor or the coil. It's when the current is going to be what? Induced in a coil. So I hope, learners, this is making sense, right? So that is what we call electromagnetic what? Induction. As long as there is that changing magnetic field. So if I say changing magnetic field, obvious, what produces the magnetic field in this case? Which apparatus produces the magnetic field, right? Is the magnet. Okay, so the apparatus that produces the magnetic field is the magnet. So if you push the magnet in and out of the coil, so the magnetic field is changing. And then as long as there's that changing magnetic field, then current will be induced in a coil. And how are you going to see that the current is induced? The galvanometer is going to deflect. Okay, so as it deflects, it shows that current is what? It's induced in what? In a coil, right? Then, what are they saying here again? If you move the magnet in and out of the coil faster, right? What will happen to the amount of current that is induced in that coil? It will what? It will increase. So one of the things that they will ask you, what can be done for the galvanometer to deflect, more? Okay? If they say to deflect more, or in other words, what can be done to increase the amount of current that is induced in this coil? Okay, so for this galvanometer to deflect more, all right, or to increase the amount of current that is induced in this coil, what can be done? But initially, electromagnetic induction, we want to produce current using the magnetic field, right? So you have seen that if there's no movement between the magnet and the solenoid, no current that is induced. Current is only induced as long as there's that changing magnetic field, or as long as there's that relative motion between the conductor and what? And the magnetic field. So now let's say the magnetic the current that is induced in this coil, it's not enough to make this bulb, for example, to do what? To glow. What can be done? What can we do to increase the amount of EMF that is or the current that is induced in this coil? One, we can move the magnet in and out of the coil faster. So to increase the amount of EMF, increase amount of current. Let's talk about current for now. So what can be done? One, increase, move the magnet in and out of the coil faster. That is number one. So if you move it faster, that is going to increase the amount of current that is induced. Two, if you use a stronger magnet, obvious there will be an increase in the strength of the magnetic field. So if you use a stronger magnet, what will happen? The amount of current that is induced in that coil is going to do what? Is going to increase. So if you use a solenoid, for example, right? So you can see this is a coil of many loops, right? So you can increase the number of loops. So if you do this again, what will happen to the amount of EMF that is induced is going to, or the current that is induced is also going to do what? To increase. So number three, increase number of windings or turns. So this is how we can increase the amount of current that is induced in what? In a coil. So, but how do we produce that current? How do we induce that current in a coil? Just move the magnet. As long as there's that changing magnetic field, as long as there's that relative movement between the magnetic field and the coil, current will be induced. And how can we increase the amount of current that is induced in that coil? Move the magnet in and out of the coil faster. 2, use a stronger magnet. 3, if let's say you're using a loop, you can use what now? A solenoid, right? So by doing that, you're increasing the number of windings or turns. And if you increase the number of windings or turns, what is going to happen? EMF, or the current that is induced in that coil, is going to do what? To increase, right? Then these are some of the things that we need to talk about: the magnetic flux and the flux density. So when we talk of magnetic flux, because we are going to use this a lot, right? So when we talk of magnetic flux, the word magnetic is from the word magnetism, all right? And then the word flux, it means flow, right? So when we talk of magnetic flux, right? So magnetic flux is about the flow of magnetism, or magnetic what? Energy. Okay, so for example, when you look at this diagram, right, you can see the field lines that are close together when it comes to point X, and then when it comes to point Y, they are far apart. Okay, so again, when I look at this, it means that the magnetic field strength is stronger here, and then here the magnetic field strength is what? It's weaker, right? So here, what are they saying? The amount of the magnetic flux varies from place to place within the magnetic field. Okay, so so for example, you can see that there are more magnetic field lines when it comes to point X, right? So which means that the magnetic flux there is what? It's stronger compared to what? Compared to Y. So when you talk of the magnetic flux, it's just the flow of what? Of magnetism, right? So then another thing which is important here, the symbol that we use to represent the magnetic flux. So magnetic flux, we use the symbol phi to represent what? The magnetic flux. And how do we calculate the magnetic flux? Although we are going to talk more about that next week, but we use the equation BA cos what? Cos theta, where this is the magnetic flux, or sometimes they say magnetic flux what? Linkage. Right, which is measured in Weber. And then Weber, the symbol for Weber, this is the symbol for Weber, is WB, right? And then we have B, which is the magnetic field, right? And then which is measured in what? This is magnetic field, which is measured in what? Magnetic field, which is measured in what? In Tesla. And then the symbol is capital letter what? Capital letter T, right? We have B, we have A, which is the area, which is measured in square what? Meters. And then theta is the angle between the normal to the plane and the magnetic field. Okay, so that is what? That is the magnetic what? The magnetic flux, right? Then another thing actually that I want us to talk about before we talk of the Faraday's law, okay? Okay, I think it's better if we start here so that maybe we don't get confused. Okay, now already we know when it comes to electromagnetic induction, right, that as long as there's that changing magnetic field, then current will be induced in what? In that coil. Okay, and current, remember, gives rise to what? To EMF. Okay, so in other words, when there's that changing magnetic flux, right, EMF or current is induced in what? In that coil, right? And that induced EMF, right? So when we talk of EMF, I think this is very, very important. We will still talk about EMF when it comes to your electric circuits, ne? But when it comes to EMF, how do you define EMF? Is the maximum, right? Amount of what? Of energy a battery, for example, can produce per coulomb of charge. Okay, That is how we define the EMF when it comes to electric circuits, right? So is the maximum amount of energy a battery can can produce per unit charge, or per coulomb of per coulomb of charge, right? So what produces the EMF this time is not the battery, okay, but is what is the magnetic field. Remember, how is it produced? Electromagnetic induction. As long as there's that relative motion between the magnet and the coil, EMF will be induced, or current will be will be induced in that coil. And that EMF induced can be calculated. This is very, very important. Then this brings us to what we call Faraday's law, okay? So Faraday's law is defined in words as the induced EMF in a circuit is proportional to the rate of change in magnetic flux, linkage. Okay, so now that induced EMF can be calculated using this equation. That induced EMF can be calculated using this equation. Okay, but how is it induced? That is electromagnetic induction. So already we have talked about how is it induced and how can we calculate it. We can calculate it using the equation E equals to negative N change in phi over change in T, right? Where E is the induced EMF, which is measured in in volts. So this is the induced EMF that is measured in in volts, and then N is the number of turns. So N is number of of turns without the SI unit, and then phi obvious is the magnetic flux, but since we have a delta phi, that is change in in magnetic flux, and then change in T, that is change in in time. So the induced EMF can be calculated using this equation. Okay, so but how is it induced? Is through electromagnetic induction, right? And that induced EMF can be calculated using negative E equals to negative N change in phi over change in T, which is change in magnetic flux over change in over change in T. Okay, then that is your Faraday's law. I'm not sure whether this is making sense. How is this EMF induced? That is, it is induced through what we call electromagnetic induction. And how is it now calculated? And then that brings us to what we call Faraday's Faraday's law. All right. And Faraday's law in which states that the induced EMF, right? That induced EMF, this is how it can be calculated. So that induced EMF is directly proportional to to the rate of change in magnetic flux linkage, or in magnetic in magnetic flux, right? So that is what Faraday's law. So we are going to talk about this next week, or calculations. We're going to do calculations next week. Okay, so initially, we have talked about current in a conductor. Around that current carrying conductor, there's a magnetic field. How do we find the direction of the magnetic field? Use right-hand rule. Now we have moved to electromagnetic induction. We want to induce the EMF in a coil, or current in a coil. How is it induced? As long as there's that changing magnetic field, then EMF is induced in a coil, or current is induced in in a coil. And that induced EMF is directly proportional to to the rate of change in in magnetic flux linkage. And this is how it is represented, or this is Faraday's law in in symbols. E equals to negative N change in phi over change in in T. So this is how we can calculate that amount of EMF that is induced in in a coil. And how can we increase that amount of EMF in a coil? We can increase it by increasing the number of turns in a coil by using a stronger magnet. We can also move the magnet in and out of the coil faster. So by doing that, we'll be increasing the amount of EMF that is induced in in a coil. But we can use this equation to calculate the amount of EMF that is induced in in a coil. So we use Faraday's law actually to calculate the amount of EMF that is induced in in a coil. All right. So here bar magnet produce magnetic field which induce electric current. Yes, that is correct, Gugu. That is electromagnetic induction. We want to produce current, or EMF, right? So how do we produce EMF or current in a coil? right? We produce that using the magnetic field, that using the changing magnetic field. So the bar magnet, what is the function of the bar magnet? Is to produce the magnetic field. And after that magnetic field is being produced, if there's no movement, or if that magnetic field does not change, if that bar magnet is not moving, EMF is not induced, current is not induced in that coil. But as long as we are going to move now the magnet in and out of the coil, we are changing the magnetic field. And obviously, immediately when you change the magnetic field, EMF will be induced in what? In a coil. If we have connected that coil through the galvanometer needle is going to do what? To deflect, to show that EMF or current is induced in what? In a coil. And that induced EMF is directly proportional to the rate of change in magnetic flux, what? Linkage. That is Faraday's law. This is how we can calculate the EMF that is induced in what? In a coil. Okay, so we'll talk about calculations next week. Okay, then, now when you look at your, what is this? Your examination guidelines, right? There's a part which says what will happen to the direction of current. What will happen to the direction of the induced current when we push the magnet in and out of the coil, right? Remember, when we push the magnet in and out of the coil, EMF will be what will be induced in a coil, or current will be induced in what? In a coil, right? That is electromagnetic what? Induction. But now, we are now going to focus on what? On the direction of the current that is induced in that coil when we push the magnet in and out of what? Of the coil. But electromagnetic induction says when you push the magnet in and out of the coil, current is induced. So for example here, what is going to happen? The galvanometer here is going to deflect, all right? So it shows that the current is what? Is induced. But now, what will happen to the direction of current when we push the magnet in and out of what? Of the coil. So this is one of the things that our learner struggles with. Okay? Now, let's look at this. Now, although this is not part of our, syllabus, we don't have to talk about Lenz's law, but actually here, it's Lenz's law that is going to explain what is going to happen. Okay? So what are they saying here? An induced current, we want the direction of current, right? We want the direction of current when we push the magnet in and out of the coil. What will happen to the direction of current? Okay? Right. So an induced current always flows in the direction, an induced current flow always flows in a direction such that it opposes the change which produced it. Yeah? An induced current always flows in a direction such that it opposes the change which produced it. Okay, so what is happening here? Right? Remember, what produces this current? This is very, very important. What produces this current is the magnetic field. Right? What produces this current? It is what? The magnetic field. Okay. So now, this magnetic field is going to change the direction of current. So already we have talked about electromagnetic induction. What produces this current? What induces this current in a coil is the magnetic field. So when I push the magnet in and out of the coil, current is induced. But we haven't talked about the direction of the current, right? So this movement of the magnet, it's what is also going to change the direction of the current that is induced in that coil. But how is it going to change? For you to be able to understand that, we have to use this law, which is called Lenz's law, although we don't talk about it when it comes to our syllabus, but actually it is Lenz's law, all right? So it says the induced current always flows. This is very, very important. The induced current, what induces the current is the magnetic field, right? So the induced current always flows in a direction such that it opposes the change which produced it. It opposes what? The change which produced it. So what produced this current is the change in magnetic field. Okay, so what is happening in this diagram? right? In this diagram, this person is pushing this magnet towards, right? It's pushing this magnet towards what? The solenoid, right? So if this person is pushing this magnet, or if the magnet is pushed towards this solenoid, obviously the current will be what will be induced. But now what is going to happen to the direction of the current that is induced? The induced current always flows in the direction such that it opposes the change which produced it. Now, so we are pushing this magnet towards the solenoid, all right? So what is going to happen to the induced current direction, right? So the induced current, right, will always flow in the direction such that it opposes the change which produced it. So let me make it simple for you. So we are pushing this magnet with the north pole. So we are pushing it towards. What is going to happen to the induced current? It's going to try to oppose this change, right? So what am I trying to say? We are pushing it towards the what is this, the solenoid? The induced current is going to oppose that. So it's pushed towards, then the induced current is going to push away, right? I'm not sure if this is making sense. So this is pushed towards, right? So this, the induced current is going to try to push it away, okay? So what does that mean, right? So it's pushed towards, and you can see this side is pushed towards the north, ne? So you have the north here. So this side, what is going to be produced is also going to be what? North. Because this induced current is trying to oppose the is trying to oppose what? The change which produced it. Okay? So if you are pushing it with the north, right? So this induced current is trying to oppose that. Okay? So it's trying to oppose that. How? So it's pushed towards, the induced current is going to push away. So push towards, push away, right? So for that to happen, it can be, if here I can say there's what here, if I can say here, this is the magnet, I'm pushing it with the north pole. This is south, so it's pushing, it's pushed towards. So this is what I have. So if I say here is going to be south, it means that what the induced current, right, is not opposing what the direction of what of the magnetic field. Okay, so the induced current always opposes the direction of what of the induced what of the induced current always opposes what the direction of the magnetic field. Okay, so if I say here it's south, it means that this is the induced current is attracting what? The magnetic field. So it's not opposing. So for it to oppose, it means that here, if it's pushed, if it is pushed with what? With the north pole, it means that even here I must have what? The north pole. So it's pushed towards, the induced current should push away. And for this to happen, if here it's north, it means that here is going to be what? North. Because north and north, or what is this? Like poles, they what? They repel. So you can see here the direction is opposite. And for us to have opposite direction, it means that I need to introduce the pole that is going to oppose, you know, the direction of the magnetic field. So if it's pushed with north, it means that what will be introduced this side is also going to be what? North. Okay? So another example, I'm pushing it again, but with what now? With the south pole. All right? It means that I'm pushing it towards, the induced current is going to push away. Where am I getting this from? From Lenz's law, right? An induced current always flows in a direction such that it opposes the change it opposes the change which produced it. It opposes what? The change which produced it. Okay, so it means that if I'm pushing it with the south pole, what will be, I'm pushing towards, then the induced current is going to push away. So I'm pushing towards the direction, the induced current is going to push away. And for that to happen, if here I'm having south, even here I'm going to have what? South. I'm not sure whether this is making sense. An induced current always flows in a direction such that it opposes the change which produced it. So for now, I'm talking about what? The poles. All right? So I'm pushing towards, the induced current is going to push away. Pushing towards the magnet, towards the solenoid, it means that the induced current is going to push away. So it's always the case. And for that force to happen, it means that if I'm pushing it towards with the south pole, it means that what will be produced here is also what? The south pole. Right? So I'm pushing it with the north pole. What will be produced here is going to be what? The north pole. Because if I'm pushing towards, right, the solenoid, then the induced current should push away. So for this to happen, it means that you must have the force of repulsion. So if it's force of repulsion, therefore, if here is north, even here is going to be what? North. I hope I've tried to explain. An induced current always flows in the direction such that it opposes the change which produced it. Okay. Then here, I'm pulling it, right? So I'm pulling away. I'm pulling away. Then the induced current is going to pull towards. Right? So I'm pulling away with the north. Then, so I'm pulling the magnet away from the solenoid. The solenoid is trying to pull it towards. To pull the magnet towards. So the induced current always flows in the direction such that it opposes the change which produced it. So it always opposes what? The change which produced it, which is the change in what? In magnetic flux or in magnetic field. Okay, so I'm pulling away this. I'm pulling away the magnet. I'm pulling the magnet away from the solenoid. This should also pull the what? The induced current should also pull the magnet towards. So which means that if here I'm having the north pole, then here I'm going to what? Have what? The south pole. So in other words, the magnet is trying to move away. The induced current is trying to say, come back. So for that to happen, if I'm having north here, then this side of the solenoid, I'm going to have what? The south. The force of what now? Of attraction. I'm not sure if this is making sense, right? So I'm pulling the magnet away. The induced current is trying to say, come back, because it should oppose that. It's always opposing that, okay? So I'm pulling it with north pole. Then on the solenoid, there will be south pole because the induced EMF or the current is trying to say, come back, right? Then when it comes to when I'm pushing, right, the induced current is trying to say, don't come in, right? I'm pushing, then the induced EMF or the current is trying to say, don't come in, right? So if I'm pushing with the north, then there will be north that is there so that there will be that force of what? Of repulsion. But if I'm pulling away, the induced EMF is trying to say, come back. So I'm pulling with the north, right? And then what will be introduced on the ends of what? Of that solenoid is going to be what? Is going to be south. Because I'm saying I'm running away. The induced EMF is saying, come back. So I'm running away with the north. For me to come back, the south must be introduced so that there will be force of what? Of repulsion. I'm not sure whether this is making sense, learners, but here we use Lenz's law, although we don't talk about Lenz's law, but you should know that that is Lenz's law. An induced current always flows in the direction such that it opposes the change which produced it. It opposes the change which produced it. It's like, for example, if I have the magnet, I'm having the south pole. This is my solenoid, okay? So I'm pulling away, right? So this magnet is pulled out of the coil or out of the solenoid. Then the induced EMF is trying to say, don't go away. So for that to happen, it means that what must be introduced this side is the north pole. So I'm pulling, so the magnet is moving out. The induced EMF is saying, don't move out. So if the bar magnet is pulled out with the north, it means that what will be produced, so that this, there will be that so that Lenz's law will be accommodated, right? It means that if I'm pulling it with the north, right, what will be produced will be south. So the magnet, I'm pulling the magnet, the induced EMF is trying to say come back, right? North, south. Same even when it comes to pushing. I'm pushing it with the south, right? The south pole is towards, then the induced EMF is trying to say don't come in. So it always opposes. The induced current flows in the direction such that it opposes the change that produces it. So, but with more examples, I think this will be understandable moving forward. Okay. Then I wanted to introduce the issue of of the poles here. Then deviation of the galvanometer needle can be increased by, already we have talked about this, learners. Okay. Then let's look at the multiple choice questions, right? The induced EMF in a coil is directly proportional to, so obvious, this is Faraday's law. It is directly proportional to the change in magnetic flux, not change, but it is directly proportional to what? To the rate of change in magnetic flux, okay? Oh, what is important here, I think we need to read, let's not rush. The induced EMF in a coil is directly proportional to the rate of change of magnetic flux inside the coil. Change in magnetic flux. This is out. It should be the rate. So we need to check this one and this one. This one is out. Remember, when it comes to Faraday's law states that the induced EMF is directly proportional to the rate of change of magnetic flux, right? So the rate of change in magnetic flux inside the coil, or the rate of change in magnetic flux outside the coil. It can't be outside the coil. It should be inside what? The coil. So the correct answer here will be what? Will be A. Then, what I was talking about here, in which one of the sketches below is the induced polarity of the coil, correctly indicated. What is happening here? A is pushed. The magnet is pushed, right? When the magnet is pushed, remember, current will be induced, but current, the direction of current should oppose the change that produced it. Ne? So, it's pushed, then the induced current is trying to resist. So it means that here, north and north should be what? Should be correct. But here, if it's pushed, remember, the current, the direction of the current should oppose the change that produced it. Ne? So if it's pushed with the north, this cannot just accept. So it's opposing that. So it means that here I must have what? North, not south. So this is out. Ne? So here is pulled with north. So it's pulled, and the induced current is trying to say, don't move away. So for that to happen, it means that here you must have what? What is very, very important here? This is north, it means that here is what? Is south. So let's just do that, because there are two poles there. It's not one pole. So this is south, this is south, this is south. So here is south, okay? And then we are pulling it out. So when you pull the magnet out, the induced EMF will say, don't pull it out, right? So if you say don't pull it out, it means that here you must have what? North. Because if it's south and south, it's like, it's fine, pull it out. There's force. I'm also pushing you away. That is not Lenz's law, right? So Lenz's law says what the induced current, the direction of the induced current will always flow in the direction that opposes what the change that produced it. Okay, so I'm pulling it with the south. It can be south-south because it's like this induced EMF agrees for the magnet to be pulled, and it shouldn't be like that. So if it's south here, right, then I'm expecting what north here, not south. So this is out. Then if it's north here is pulled, I'm expecting south because there must be that force of attraction to say don't go away. So then this is also what out. So the correct answer here will be what? Will be A. Yeah? So with more examples, I think we'll understand this, learners. Right. So a bar magnet can be moved towards or away from a solenoid, yes, to induce the EMF or the current in a coil. Which one of the following factors or actions will increase the deviation of the galvanometer? So if they say increase the deviation of the galvanometer, they're trying to say to increase the amount of EMF or the amount of current that is induced in that coil. So those three things that I've counted, in using a stronger magnet, increasing the number of turns, moving the magnet in and out of the coil faster, right? So this one, the first one is out. Use the solenoid with a smaller diameter. No, use the solenoid with fewer turns. If the turns are fewer, it means that the galvanometer is going to deflect less, right? So it means that the amount of EMF will be less, right? So it can be. Then using a weaker magnet, we are decreasing the amount of EMF that is induced in that coil. But moving the magnet faster towards or away from the solenoid, then that will be the correct what? The correct answer. Okay. So we are not going to look at all the multiple choice questions. Let's look at the structured questions because we are left with few minutes. The current flows in a conductor from positive to negative. So from positive, so it means that here we have what? We have negative because I have positive there, right? Use the correct rule to show the direction of the magnetic field formed around the compass that is underneath the conductor. Okay, so this is the conductor, and in this conductor there's current that is flowing, and the current is flowing from positive to what? To negative. So that is conventional what? Current. So the direction of current you can see is into the page. All right, so this one is into the page, right? So if it's into the page, use the rule. Which rule are we using? Right hand rule. So right hand rule, the current is into the page. Remember, this is a straight conductor. Okay, so it's into the page. So if it was like this, that is going to be what? Out of what? Of the page. So into the page using the right hand. So it's into the page, and then look at my curl fingers. So the curl fingers pointing in a clockwise what? Direction. They are pointing in a clockwise what? Direction. So it's going to be what? Clockwise what? Direction. Clockwise direction. Okay. Then show the direction of the magnetic field around the following conductor. So already you know that across the direction of current is into the page. So into the page, right? And we have to use what? Right hand rule. Again, this is into the page. Remember, the cross is out of the page. The dot is out of the page, and then the cross is into the page. So here is into because I see a cross here. So it's into the what? The page. Then into the page again. Use your right hand. The curl fingers are pointing in which direction? Clockwise what? Direction. So it's clockwise. Clockwise what? Direction. Clockwise direction. Okay. Then this is a solenoid. Label the north pole and the south pole of this current carrying solenoid. So this is positive to what? To negative, right? So this is what we are going to have as the direction of what? Of current. So they want the direction of the magnetic field here. And which rule do we use again? We use right hand rule. But remember, you need to hold it. And when you hold it, bend your fingers, or the bent fingers should follow the direction of the conventional current. Okay, so they should follow the direction of the conventional what? Current. Okay, follow the direction of the conventional what? Current. It means that when I do that, you can even do that at home. This side I'm going to have my north, and then this side I'm going to have what? My south pole. Okay, because remember the fingers are in the direction of the current, conventional current. So the way they are bent should follow the direction of the conventional current, and then wherever your thumb is pointing, it should point what? The north pole. So hence this side I will have the north pole, right? Then this one, a magnetic field is produced when current flows through this open coil of a wire. Give 3 ways in which the magnetic field can be what? Can be increased. 3 ways in which the magnetic field can be increased. So we can increase, I think here they were referring to the current, ne? I think we need to check that, ne? Because we can only increase the magnetic field by using a stronger magnet, okay? But if they were asking about what? Increasing the current that is induced. Oh, no, let me read again. Sorry about that. Yeah, because it's not electromagnetic induction. The magnetic field is produced when current flows through this open coil of wire, right? Give 3 ways in which the magnetic field can be increased. Oh, now we are increasing the magnetic field. The magnetic field, learners, can be increased by using what? A stronger, not a stronger magnet, but by using what? In this case, by using what? Source of power. Of power with high voltage, right? 2, in this case we can use a source of power with what? With high voltage. And if they're saying 3, let's just check, because unless if it's going to be all right. So here, increase the strength of the magnetic of the current. How can you increase the strength of the current? You can increase the strength of the current by by using a source of power with high power or high voltage. That is how we can increase the strength of the current. You can add more windings, right? So increase the number of turns. Add an iron core to the coil. So but these 2, I think we are familiar with these 2. Increase the strength of the current. How do we increase the strength of the current? Maybe by using the source of power with high voltage or high power. Then add more windings or increase the number of turns. So with this one, I think we need to add an iron core an iron core to the coil. So by doing that, we'll be increasing. I think this is another thing that we need to talk about, and I didn't talk about this, learners. How can we increase the amount of the magnetic field or the strength of the magnetic field? Because remember, around a current carrying conductor, there's magnetic field. So how can we increase the strength of that magnetic field? So these are the 3 things that you can do. You can increase the strength of the current. How? By using a source of power with high voltage. You can increase the number of turns or windings in a coil. For example, if you're using a straight conductor, you can move from a straight conductor to a loop. Or if you're using a loop, you can move from a loop to what? To a solenoid. So by doing that, you'll be increasing the strength of the magnetic field that will be produced there. Okay? Then also add an iron core to the coil. So by doing that, you will be increasing what? The strength of the magnetic field. I hope it's making sense. So I don't want us to confuse increasing the strength of the magnetic field and the amount of the current or EMF that is induced in a coil. How can we increase the amount of the EMF induced in a coil? Increasing the number of turns, moving the magnet in and out of the coil faster, and then 3, use a stronger magnet. Then how can we increase the induced magnetic field or the strength of the induced magnetic field? When there's a current that is flowing through a conductor, remember there's magnetic field that is produced. How can we increase the strength of that magnetic field? We can increase it by using what? by adding what? An iron core in the coil, add the number of windings, or increase the number of windings, or what, or turns in a coil, and also increase the strength of what, of the current. Okay, so those are some of the things that we need to what, to do, right? So then question 6, a coil of wire is connected to a sensitive galvanometer as shown in the diagram. Ne? What is observed when the magnet is moved towards the coil? Obviously, if the magnet is stationary, remember, nothing is going to happen to that galvanometer nickel, right? But what will be observed, right, when you move that magnet towards the coil? The galvanometer is going to deflect, right? Or the galvanometer is going to deviate, okay? Or galvanometer nickel is going to what? To deflect. Galvanometer nickel, which is this, will deflect. Right? Explain why this occurs. Obviously, here we have to use electromagnetic what? Induction. Use electromagnetic induction. Obviously, you explain why it occurs. According to Faraday, as long as there is changing magnetic flux, as long as there is changing magnetic field, as long as there is changing magnetic field, current will be induced in what? In a coil. So they explain why this happens. Explain why the galvanometer nickel deflects. It deflects because there is change in magnetic field. And if there is change in magnetic field, current will be induced in a coil. That is electromagnetic what? Induction. Then describe what happens when the speed of magnet is increased. So when you explain what will happen when you increase the speed of the magnet. So if you increase, or if you move the magnet in and out of the coil faster, what will happen? The amount of EMF induced in a coil, or the amount of current induced in a coil will what? Will increase. Or the deviation of the galvanometer will what? Will increase. It's what is going to happen. Describe what happens when the speed of magnet is increased. So in other words, they're trying to say to you, when you move this magnet in and out of the coil faster, or in the coil faster, or out of the coil faster, what is going to happen? What are we going to observe here? The galvanometer, or the deviation of the galvanometer will increase, right? Or you can say induced current will increase, or induced EMF will what? Will increase. Okay, then I think for today we have covered a lot. So let's end here. I know it's a too abstract topic, but I think I've tried to explain it, and I believe that you got something, and you understood what we did. If you didn't, then please also consult your teachers. They will also assist when it comes to these topics. No, I know it's a challenging topic though, but yeah, thank you so much. See you next week. Bye-bye.